Welcome back for semester 2 of organic chemistry. Our first experiment is going to be experiment number 35, the directive effects in the bromination of vanilla. Vanillin is a compound that you're very familiar with it. It's typically the compound that gives most of the taste of vanilla. But actual pure vanilla has a bunch of compounds in it. Uh, but artificial vanilla, for the most part, is going to be um, mostly the vanillin compound, and it is a compound that does give you that sensation of vanilla. Once again, pure vanilla has other compounds in it that we're going to be looking at. So in terms of our experiment, what we're going to do is we have some materials. We're a large paper company in this case, and if you treat some of the materials from a paper company, the chemical called lignin, one of the products that you can get is vanillin. And it turns out that what he wants to do is Woody Aspen is the name of our director at Pulp Chem, wants to develop a new product from vanillin that might be marketed commercially. He's found a way to add bromine to the vanillin compound, and you can see the structure of vanillin here. And you can see that this is a benzene ring here, and it has 3 substituent groups on it. Well, it turns out that these substituent groups will decide when we put the bromine on based on what they do. They'll decide where that bromine goes. If you'll notice, we have 3 possible compounds that could go. We could put the bromine here, we could put the bromine here, we could put the bromine here. So our goal is, by knowledge of information I'm going to give you, we're going to try to predict, and it's going to turn out that all 3 of those compounds have a different melting point. So we're going to produce the compound, we're going to brominate, and there will be 1 bromine that will be put on the ring, and it will go to one of those 3 positions. We're going to predict which one it should be, and then what we're going to do is we're going to determine if we were correct in our prediction of where we thought it would go based upon the chemistry. So it turns out that once you know what's on a benzene ring, that those substances are going to determine where different molecule or anything that's added to the ring can go. And we're going to call those 3 positions. If I had 1 substance on a benzene ring, like we're going to call it compound A here, or molecule A, or just an atom, if it goes to the position next to that, we call that an ortho product. If it is 2 away from the original, that's meta. And if it's opposite from the original material, that's called para. Now, what we're going to do is we're going to do electrophilic aromatic substitution. And an electrophilic aromatic substitution, in essence, there's an H at each one of these positions. We're going to take one of the H's off and replace it with an electrophile. So in each of these cases, these electrophiles that are going to come there, because remember, benzene has that rich pi cloud of electrons that it can attack this, it's going to come in and attach itself to those groups. Now, it turns out when there's something on a benzene ring that it turns out there's different compounds. For example, if we take this compound here, and you'll see it's benzene with a CH3 group on it, toluene. If we take toluene and that CH3 group and we add bromine to it, there are 3 possible positions it could go to. And the other product will be HBr if we add Br2. Now in our lab, we're going to add bromine, but we're not going to add it in this form because this is a very noxious chemical, straight bromine. And the catalyst is iron tribromide here, or ferric bromide, or iron 3 bromide, whichever way you want to refer to it. Well, it turns out that what we're going to do is we're going to use KBrO3 and hydrobromic acid, HBr. What that's going to do is the reaction between those two is going to create the bromine, and we don't have to use this noxious bromine. We'll do a reaction between KBrO3 and HBr. So that's something you want to keep in mind, is that we're going to produce the bromine in situ by doing that, as opposed to having to add the noxious bromine. But this is a very common way that it's done. And then what we're going to do is we're going to look at these, and typically you can look up lists of these. I will give you a list in class of different what we call ring activators and ring deactivators. A ring activator makes the reaction happen faster than if it was just straight bromine or straight benzene. A ring deactivator makes it go slowly. It turns out that all ring deactivators are meta directors. In other words, there's 3 possible products, but if we had a compound, if you'll look this time, the results of this experiment are we get 40% the ortho and we get 60% the para. It turns out that if we look at all the resonance structures of these compounds, that these two things are very similar. So if something's an ortho director, it's usually a para director. So we call those ortho para directors. And generally, you're going to get 2 products. If something's a meta director, like for example, if we have a nitrate group on the ring, notice this time it was a CH3 group, this time it's an NO2 group. When we add nitric acid and put another NO2 on, it turns out that 93% goes to the meta position. You get only 1% para and about 3% this. So essentially, most of the product is this meta product. Now, so ring activators are materials that don't withdraw and don't pull electron because of high electronegativities. They don't pull the electrons away from the ring and allow for resonance structures to form. So if something's a ring activator, it pumps electrons into the ring and allows for resonance structures to form. So that's essentially the basic difference between the two. All 3 of those products would have different melting points. So what we're going to do is look at our material, and we're going to look at the list of ortho-para directors. And we're going to know that, for just as an example, if we look at our list, we see that some common ortho-para directing groups are OR group, NR, R, and X. Now, here's something weird. X, which are halogens, actually are highly electronegative and do pull electrons away from the ring. They're actually deactivating. But they're still ortho-para directors because of all those electrons around them. Those electrons can be used to form the resonance structures. So even though they have a high electronegativity and are pulling the ring away, the fact that they have so many extra electrons available in their outer shell still makes them ortho-para directors. In lecture, you'll probably go through that and how to draw the resonance structures of those. We won't spend the time here doing that. Meta-directing groups, you can see it's typically NO2, NO, things with a lot of electronegativity, things with O's and CX, where the halogens want away from the ring, then that pulls that electron density away. Nitrogen, sulfurs, all of those. So if we go back to, we're going to put bromine on the ring. Whoever's jumping on does not determine. Whoever's jumping on does not determine where they go. It's whatever's on the ring determines where things are going to go. So if we look back at our list again, OR, which could be H as well, OH, OR, and then we can look like C double bond OR. That's also something that's deactivating. I'm going to run out of time here, so I'll go to part 2, and we'll see you just back here in a moment.